Okay, so now let's go on to taking a look at the demo as to what we are going to achieve. And this is like only the first step of potentially many. So what you see on the screen, the important bits here are a look at, well, okay, let me just change color here. A look at the while loop here and look at the while loop here. So both of them are while one, so essentially infinite loops. And then this function right here, we are calling it task 2. This function right here, we are calling it task 1. Now, much like the pharmacy example that we looked at, our CPU is the pharmacist, the guy behind the counter, and task 1 and task 2 are essentially the customers, the folks who have come to get the medicine, so to speak. And what they want to do is just simply increment a variable. Right? Task 2 wants to increment B, task 1 wants to increment A. What I'm going to do now is first just blindly run few things and then explain what happened, how does it relate to reality and all of that. So I'm going to first do like make. Oh, okay, I'm supposed to do it from the port, so make. And this is compilation, and after compilation we got this main.elf, right? That's the file that was of use to us. And then we do something called make QEMU, and as we do that, okay, there is like blinking cursor on the screen. Perfect. After this, what I want to do is to go to this debug button here and press the play button. And again, we'll explain all of what is happening. Then what I want to do is go to the main.c file here and first off put two breakpoints. So these red dots are representing breakpoints, and what I'm doing is I am essentially debugging. So I started a debug session, and here we see very quickly CPU internals.
Piyush, just for
Mhm.
just for people who might not be aware of breakpoints, a quick 30-second overview.
Oh, sure, sure. Thank you. So what we are doing here, what's happening is the CPU is going to execute code. And what we have is we have some sort of magic around it that is called GDB, the GNU debugger. And what this GNU debugger can do in the current scenario is it can control the execution that the CPU is doing. So what then happens is at will we can say, hey CPU, pause, stay where you are and
Hmm.
expose to me your internal state. So
Hmm.
that is available here, right?
Hmm.
So we can manually pause it at will, which I'll
Hmm.
show in a bit. But the other thing GDB allows us to do is it says, hey, tell me what code are you running on the CPU? And we
Hmm.
say we are, doing, we are going to run main.elf.
Hmm.
We're going to load that as the firmware and run that.
Hmm.
Then what the GDB allows us to do is it says, okay, I am now aware of the source code. I'm aware of, because of the debug symbols included
Hmm.
in this binary, I'm aware of what location has what code. And
Hmm.
so what I can tell GDB is, hey, could you stop or pause the CPU once line number 6 of main.c is being executed? The assembly program or the machine code relating to this line is being executed. Could you stop or pause the CPU? So that is what a breakpoint is. A breakpoint is we are telling, hey, once the CPU comes to execute this instruction or the machine code related to the C line, what GDB should do is pause the CPU,
Hmm.
right? Stop the execution and extract the internal information of the
Hmm.
CPU. Again, we're going to take a look at all of this: internals of the CPU, what M class CPU is, what all should you know, what all should you not know, all of it. This is just a demo, and what I wanted to show was the CPU juggling between two,
Hmm.
so to speak, tasks. Right now, the CPU is stuck here. So when we see a highlighted line here, the CPU right now is booting up and it's about to jump into the main function.
Hmm.
And the main function is down here. Now, we
Hmm.
don't care about the contents of the main function. maybe just the fact that we are creating or letting
Hmm.
the system know about two tasks, task one and task two, and after that we are saying, hey, okay, start the scheduler now.
Hmm.
How the scheduler starts, what are the prerequisites, we will discuss all of it.
Hmm.
Okay, when I click this play button, the continue button here, what will
Hmm.
happen is we are freeing the CPU to run
Hmm.
freely. And as I do that, well, it just came and got kind of entered task two.
Hmm.
Right. So I'm going to remove this
And because we
breakpoint.
had programmed the breakpoints earlier,
Yes.
instruct the CPU to pause at line 13, it
Right.
did
Yes.
this. That okay.
Right. So what it did was it started to execute task two first. So it is now stuck here. Now when I, let's say, uh, move it uh, further, you'll notice that it has now started to run freely again. Now when I hit the pause button, well, what happened? Okay, it's still running here. If I press the play button, what happened
Hmm.
was it was within task 2, it escaped that, and now it is within task 1.
Hmm.
Long story short, it was executing task 2 for a while, then it came and started to execute task 1. This is the first time task 1 is getting a chance. Now I'll let it run for some time, right? And I'll arbitrarily pause it. It's still within task 1. Let it run for some time, pause it. Now we
Hmm.
see it in task 2. If I were to put a breakpoint here and let it run now, you see it
Hmm.
came back here. Now if I put here and let it run, it came back here.
Hmm.
What's happening is every few milliseconds it's juggling between both of them. And if you notice, well, this value of b here won't be
Hmm.
same, right? So if I pause it and again it's a 2,
Hmm.
see it went from 8 something to 9 something. That tells me that it was executing and incrementing me, right? So this is then a visual representation or like a practical demonstration of the CPU juggling between task 1 and task 2, and
Hmm.
both of them are trying to simply increment a variable. Now this incrementing a variable is similar, a very like a very crude, very simple, useless, trivial kind of state machine which does nothing. But what we can do is have, let's say, one LED controlled
Hmm.
from here and one LED controlled from here, or the switch being monitored from here and LED being controlled from here. So all of that can be done. Okay, now let's peel the onion a little bit as to
Before
what
that,
happened.
I
Yeah,
can I
go ahead.
just because at this point, an engineer in me, and I want to sort of approach to the folks out there and make them appreciate the beauty of this.
Yeah.
Is if let's say our goal was to increment A and B, right?
Hmm.
And it
Hmm.
should be done independently out there. And we'll come back to the independent part later. But let's say we had these two while ones in our main function directly,
Right.
just one after the other. There was no
Right.
way the control would have gone to B. I mean, it would die when
Right.
you do something, and it would not. So it
Right.
would always be A plus plus, A plus plus, A
Right.
plus plus.
Right. So a while one here and a while one here,
Yeah.
one after the other.
The
Well,
other
once it is stuck here, it just stays because it's
stays
while
there.
one.
Yeah,
Yeah.
yeah. And the
Well.
beauty is that
Hmm.
as far as the task one and task two are concerned, they think, hey, I am in while one. No one is able to just come out there and take any control from me.
Yeah.
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 But then
Yeah.
there is some entity, some god level entity, at least for them, which does that without them knowing about it. And that is
Exactly.
what the scheduler is, and that's the beauty of it. And I hope people out there also appreciate. And in fact, I'm getting goosebumps right here. Like it's some engineering, some creative engineering which has gone there.
Oh
Who
yeah, it's a very clever trick that people are
right.
using here to
And
achieve this.
absolutely right, right. And precisely that. And the beauty is, even if this is not like enough, the beauty of this entire this model, like we have two tasks working independently, is why the world is at this place. It has
Yeah.
developed so exponential. And I'll tell you why, right?
Yeah. Yeah.
Because you
Yeah.
don't need a single guy working on the entire code base. You can independently give out these tasks to multiple developers. Like, hey, you just worry about your task. There is
Yeah.
some entity out there which is going to manage the CPU, between them. So
And your task will just run. assume that you own
You are
or
the
have.
only one.
Yeah,
Exactly. And
correct.
that sort of increases the development effort many folds. It doesn't have to be serialized anymore. It's like
Right.
in
Well,
manufacturing what Henry
Mohammed, I would want to correct, instead of increasing the development load, what it does is it parallelizes.
parallelize. Yeah, yeah, yeah. That's what I think I meant, but I might not have used the words correctly. So I like to think of this as sort of the industrialization which Henry Ford's assembly line
Line
brought.
did, right?
Yeah.
The parallel
I
manufacturing of different parts.
I could not stop from appreciating.
The engineer in you jumped in. Nice. And I suppose this is why we wanted to have like a joint session wherein we both talk, and hopefully this is
Yeah.
also how the learner stays engaged. Okay, great. So what is going on here? Everything seems to be running within like a VS Code kind of an environment. So
Mhm.
what is happening? So there are few moving parts here. Let's go to well, first off, let me just introduce as to what all is happening. First off, before I even introduce any of that, let's come here
Mhm.
and talk about something called QEMU. So QEMU is a software, and it's called Quick Emulator. What it is capable of doing is it is capable of acting like hardware, which then means it mimics. And just correct me, the spelling here, is
Hmm.
this right? Okay.
I think K won't
The
come.
K won't be there. Okay, perfect. So it mimics the states
Hmm.
of hardware. So, Mama, do you happen to have the board with you?
Yeah, I have it right here.
Okay.
So this, if you can, yeah, if it's
Yes.
visible to the end users, yeah.
Yeah, yeah, it's visible. So the board that we see Mohammed holding,
Hmm.
that's one of the STM32 development boards. Mohammed, you can keep it aside now.
And
So
here, this is the main chip, which
yes,
has the ARM Cortex M on
M3.
it.
Yes.
M3, yeah.
So M3. So what we saw Mohammed holding was one of the development boards, and my claim is QEMU as a software allows us to mimic exactly that board, right? Which means it mimics the M3 processor on it, the memory on it, the I/O, the timer,
Hmm.
everything, and it mimics in the sense that it is capable of consuming our main.elf file, which was the firmware, so to speak, which was the binary code that we intend on putting onto that hardware
Hmm.
device. So it can take this code and walk through that code line by line as a CPU would do, and then execute exactly as the way that board would. Right? So that's the idea of QEMU. And so what we have done here is we are using QEMU, and whatever demonstration you saw, QEMU was emulating the board that Mohammed showed you, and it was essentially then running our firmware. And emulation environments are great for development. Without dependency on a hardware, we can get going, we can do our development, and once we are convinced that things look all right functionally, we can then take this code and deploy it on hardware. Okay, that's the idea. And then the board that we are asking QEMU to emulate is the STM32 VL Discovery, and that's exactly what Mohammed was holding. Okay, now let's come to files. What's happening here, and why all of this is so magical? So first off, let me go ahead and do make clean so that the object files and the unnecessary files are out of the way. So what we have here, the port directory, that's where we have we have files or code that we as the user of FreeRTOS need to
Hmm.
FreeRTOS need to provide, right? So then we have some assembly file, we have a header file, we have a C file and a linker file, well, another C file. So two C files, one header file, and one assembly file,
Hmm.
right? And then we have this make file which helps us with automation. Instead of executing too many commands manually, what we can say is, hey, make file, I'm telling you how to execute multiple commands as a result of one command. And I again want to quickly show. So when I just do make, we see that so many instructions are being executed, shells commands are being executed, and so makefile is used for automation. Great. So I just want to summarize once again. So let me do make clean. Make clean will wipe out all the object files for us, and we'll see details of all of this, by the way, right? So no worries. The boot.s has code related to boot up of the CPU, the M class CPU. The main.c has the initialization code and the tasks, right? The port functions.c has few functions like memcopy and memset that we need to implement. The linker script file here, the .ld file, has information related to which part of code sits where in the memory. We'll talk about that as well. And the header file here as well, just constants and things like that, some configuration related information. Now, if I were to jump into the main make file, you'll see that there is like boot.o, which is essentially boot.s converted to boot.o. So if you just replace the .o with .s and .c or .c,
Mm.
you will essentially find the names of different file here. So these three files then are the source code we write, we as the users, and these four files here are coming from this directory called FreeRTOS Kernel, right? So tasks, list, heap, and port. And these three files or four files are included as part of this directory here. And if you see, this directory is the actual source code of
Mm.
FreeRTOS, and it has too many things in it.
Mm.
There are just too many files. And of those files, what we are going to prove to you is that only these four are
Correct.
relevant and important, right? And that is the entire journey that we are going to take on now. So we'll try our experiments on QEMU. QEMU is a software that mimics the behavior of the hardware board. The hardware board is what Mohammed showed us a while back, the STM32VL Discovery. And then we are going to write these 4 or 5 files on our own, reason about them, and
Mm.
also pick exactly the files from FreeRTOS that are required. And
Uh,
towards the
Files
end,
10 to 30, right? The four files.
yes, 10 through 13, the
30.
four files.
Perfect. Mm.
And what we'll also do towards the end is throw away all the unnecessary code
Mm.
from FreeRTOS and just retain the very few minimal files that you would require to achieve the FreeRTOS port, to get a scheduler going. And yeah, that's about it. Mama, did I miss anything?
No, but I'm quite excited.
Okay, fine.
Yes.
And we are going to,
We can get one more clarification is the
yeah,
reason why we are straight away not trying it on a hardware is first, we want to go through an actual journey where you mostly use an emulator to make things functional, and then at the end you try it on a hardware. That would
yeah,
be one. And secondly, because of not many people out there might not have the discovery board, so we wanted to be accessible to almost all of you,
yeah.
and that was the reason why we chose to work on emulator.
All right. So yeah, with that, we'll jump into starting from scratch, booting the CPU, reasoning about the CPU, including the FreeRTOS kernel, and then going from there.
Mm.
All right. So with this, welcome aboard, and we'll see you in the next one.
The next one, yeah.